Hello, good evening everyone. This is Krishnakant Roy, and today we are going to discuss about the test of stationarity. In the previous videos, you must have seen what are the different criteria of a stationary series. So when you're dealing with time series data, it is often observed that in the time series data, you find the data is non-stationary in nature. And there are three criteria for stationary or non-stationary to find out. But the problem is that the moment you find the data is the series is non-stationary in nature, then you face a lot of difficulties, like you cannot apply models like ARIMA, you cannot generalize it, the ability to forecast will not be efficient. So there are problems. So first and foremost thing is to identify whether a data series is stationary or non-stationary. If the data is stationary, then it is, yes, it is it can be used for modeling purpose. And if it is non-stationary, then you need to do something. So today we are going to focus on the discussion of whether a series is stationary or non-stationary. So basically, informally, graphical method is there, which was already discussed, that if you plot any series and if you find a trend or season, then probably you can say that the mean can vary or the variance can vary over a period of time, and there is a possibility that the data is non-stationary. So those graphical methods are more like informal methods, but in the initial stage, you start with the graphical method and then you suspect whether there is stationary or non-stationary, and then you move towards more formal kind of method. So today we are going to discuss a very famous test for stationarity that is called as Augmented Dickey-Fuller test, right? So I'll just give a background about this. So Dickey and Fuller have written a paper in 1979 about how to identify whether a series is stationary or non-stationary. And the starting point was that. And then later it was modified, that I'm going to discuss during the video, that now it is called as Augmented Dickey-Fuller test. All the softwares, major softwares like SPSS, eViews, or you can call it R, Python, this test is already there because it is widely used. All right, so today our video will be focusing on the theoretical aspect of the Dickey-Fuller test. What exactly is Augmented Dickey-Fuller test? So let us start with a very simple, you can call it equation. All right, so assume that y t is equal to alpha plus beta y t minus 1 plus mu t. So this is a AR process of one, you can say one lag. We have already discussed this in the previous lecture. Now you can see this beta. This beta is a coefficient. Now this beta, if you consider if beta is greater than 1, which implies if beta is greater than 1, that simply implies that the relationship between yt and yt minus 1 is going to be explosive series. So it will keep on increasing like an exponential. So definitely explosive series simply means that it is going to be non-stationary in nature. If beta is, let's say, less than 1, then you call it the relationship over a period of time die out. So you call it die out series. Die out series, and you can call it, this type of series are stationary in nature. Stationary in nature. And another possibility could be beta is equal to 1. All right. Beta is equal to 1 simply means that there is a pure relationship, pure trend between yt and yt minus 1. So you can call it pure trend. And this type you call it non-stationary series. So ideally we deal with these two. We check for stationary, and we try to intend to find out whether beta is less than 1 or equal to 1 based on some confidence interval and all that. So that's the background of, you can call it a series. How do we identify? Now, when beta is the last option, when you see when beta is equal to 1, it is also called as unit root series. So if that means here, just remember that if a series is unit root, that simply means that it is showing a trend and it is non-stationary in nature. The series is non-stationary in nature, right? So majority or many of the series which you find actually is non-stationary in nature, that we are going to experiment in a subsequent video. But at the moment, we can, I mean, simply consider, let's say now consider a simple without drift equation. Now consider, let's say yt is equal to beta t minus 1 plus mu t. So this is without a drift, without intercept. I have considered this equation, a simple equation, just to get, just to derive the contribution of augmented Dickey-Fuller, or you can call it a contribution of Dickey-Fuller. Right now, what you do, subtract both side by t minus 1, a mathematical manipulation, t minus 1. All right. So we get yt minus yt minus 1 equal to, call it beta yt minus 1 minus yt minus 1 and then plus mu t. All right. Or you can write this as, this is nothing but the change in yt. So you write this as change in yt is equal to this. You can take beta minus 1 common. So beta minus 1 yt minus 1 plus mu t. All right. Consider beta minus 1 as gamma. So consider beta minus 1 as gamma. All right. So now you can write as change in yt is equal to gamma yt minus 1 plus mu t. So this equation, you can call it, this equation was contributed by Dickey and Fuller. Dickey and Fuller. This was the contribution. Now from here, so how do we test or how do we identify? So from here we see what exactly is gamma. And that simply means if, now you can realize if let's say beta, look at this equation. All right. If beta is equal to 1, the series is unit root and gamma will be 0, and this you consider as for this, what will happen? The series will be non-stationary. If beta is, you can call it less than 1. If beta is less than 1, then gamma is going to be less than 0, negative, and then you call it series is stationary. All right. So that is how you identify based on this equation whether the series is stationary or non-stationary. All right. Now, as I said, this is the theoretical aspect of Dickey-Fuller. One should know this. Then it will give you, you can call it a clear-cut idea. But now this this equation have three different aspects to it. Number one, you can write, that is, this equation is, let's say, number one, you can call it, which has no intercept or no drift. Number two, you can call it, a modified version of this is y, change in yt is equal to, you can put an alpha plus gamma yt minus 1 plus mu t. That is second variation. And third is the change in yt is equal to, I cannot write t here, is equal to alpha plus, there's a, you can write as phi t plus gamma yt minus 1 plus mu t. This is third. So there are one, two, three variants. Now in the first equation, you can see that there are no, you can call it intercept or drift component, and no trend component, time component. In the second equation, you have the intercept, but you don't have time component. In the third equation, you have drift or these intercept and the time component. Depending upon the situation, depending upon the requirement, anything can be used. But we widely use this equation. Definitely, it is not sure that all the time you have to use this. But yes, this is widely used, which you call it change in yt equal to alpha plus gamma yt minus 1 plus mu t. All right, so this is one thing, one should know. I hope you just make a note of this equation, and this is what we are going to use when we'll run a software with this. All right, so what will happen, I'll just quickly tell you about the other equation, that this was contribution of Dickey-Fuller. All right, now what exactly is then augmented Dickey-Fuller? So what I'm going to write, the equation of augmented Dickey-Fuller now. All right, so augmented Dickey-Fuller was a modified Dickey-Fuller test, you can call it, and the modification was, I'll quickly write so that you can do. Modification is that, I'll write in a red ink only. So delta yt is equal to alpha plus time component t plus gamma yt minus 1 plus, there is another component, summation, you can call it some I, then you can call it change in yt minus 1, and not 1, we are writing generalized, so t minus I, and I is equal to 1 to, let's say, n, and this is also I series coefficient, plus mu t. So this equation is, we call it augmented Dickey-Fuller equation. All right, now we'll quickly see. Now only thing is, from the Dickey-Fuller, this component is added. Why this component is added, I'll quickly tell you the rationale. The rationale is that it was suggested that to increase the goodness of fit of the model, to increase you can call it the results, so they have added one more component, which is nothing but change in yt minus I. Now this can be anything. You can go up to many lags, t minus 1, t minus 2, t minus 3, t minus 4. What is the rule? The rule is that whatever, I mean, it's not fixed, but if, let's say, you're dealing with 40 years of data, so 1/4. You can go up to 1/4 of 40 years is 10. So t minus 10 up to, you can go and you can check whether the data series is stationary or not. So this is how the entire series, this is the Dickey-Fuller equation looks like, and you can write any of the component if you don't understand in the comment section. But at the moment, just reflect that what exactly it does. So you start with one series only, and then you build upon it. All right, so this is a theoretical lecture. I hope you like it. And in case of any doubt, you can ask me in the comment section. Thank you for watching, and I'll be giving you more details in the next video.